Hello everybody, how's it going? Alright, somebody forgot to put his webcam in the right place. Yeah, welcome to another stream. Hope we're all doing well. There we go. So, last stream we added a visibility buffer so we could basically render opaques out using an atomic min with U64 with the depth in the high bits and a ellipsoid index in the low bits. So this right here is actually our tile binned ray tracer rendering out this, and I actually spent a little bit of time off stream to carry on and just get the visibility buffer up and running, but there are some bugs with it. So the visibility buffer is rendering. There was a debug pass that we do. Let's just find it. So here's the ellipsoid indices. Yeah, it's a little bit buggy. They're kind of showing up there. And then there's also, yeah, I think there is a depth, but that's already been, yeah, if we move around the screen. Ugh, yeah. Maybe as they get bigger, it's fine. No, not really. Oh, no, I have to use the hash view. Right, there we go. Yes, it does work when they're bigger. And then, yeah, it's a little bit buggy though. If we pause it, I think it's with multicolored stuff in our face. There's some some sort of issues here, I think. They're cut off like a rectangle, which means it's likely to do with there not being enough pixels trying to render the ellipsoid. So we'll look into that. But yeah, I think what we'll do first is we'll massage the code a bit. Do a bit of code massaging, you know. Welcome, folks. And make it such that the visibility buffer will actually render to the screen rather than us having to look through the texture viewer, right? And that will help us be able to debug. And if we scale it down to one ellipsoid, we can sort of move it back and forward from the camera and really trace down the bugs a lot easier, because there's basically 7 different ways to render an ellipsoid depending on what size it is. So while we're doing that code massaging, we'll give a bit of a recap on how the thing works. Right, so with render models, we basically, so it's got the tile binning and the binning ray tracer in there, and then it's also got the visibility buffer version as well, which doesn't quite fully work, but hopefully we'll get it working today. And right now it just emits, emits the ellipsoid index and the depth, and then there's a debug way to sort of split them out into 2. So what we're going to want to do is probably split this out into so this is we probably want to have one which is called not render models, but this one might be called emit ellipsoids models. I'll just say ellipsoids. So this emits the ellipsoids to render. Yeah, my laptop's not on today, so I'm going to have to flip that between chat. And then, right, so this is tile. Okay. Then I think we'll need another one. This payload isn't used here either. So this one will be called render models tiled. Right, so eventually this one will just be the transparent ones. Or render ellipsoids transparent. Yeah, eventually that's what it will be for. And then there'll be some tile bend thing and sorted front to back and all this. And then we'll have an opaque one where it'll be done with a visibility buffer, I think. I've looked at the numbers briefly. It seems like they are quite good, but maybe there's a bug or two which is making it so that it's better than it is. So yeah, we might end up. We still want to see if the visibility buffer is the way we want to go. If not, we'll just do the tile-based renderer. So let's grab all this visibility buff stuff and we'll do a bit of a recap on how it works, because we'll be working more on it. Okay, so we need these sort of scopes. Oh. So this be render ellipsoids. Yeah, I could just call it render opaque, right? Why'd I have to say ellipsoids? Emit instances, maybe? Emit ellipsoids will still be fine, I think. Render opaque. Render transparent. Because it's got to show up in the profile, you know? So the smaller the name, the better, really. But I guess that'll be a big section anyway as a scope. Alright, render transparent. Oh yeah. Alright. So I think we're looking good there. Now, what we are missing still is the material shading part of the visibility buffer. So, right, I guess let's give a brief recap on what visibility buffer is. So, a visibility buffer is basically like it's an approach to replace a G buffer for deferred rendering, and it tries to make overdraw like, so you're going to get some level of overdraw whenever you rasterize things on the screen, when you're not doing things in a sort of a tile binned way, right? When you're not making screen tiles that have their own arrays, and you go over front to back of the things to render in early out, you're going to get overdraw because you keep rendering stuff to the same pixels. So what a visibility buffer is designed to do is you only write out the most minimal amount of stuff. Now we're still doing this with compute. So what we do is whenever we have an ellipsoid that we want to render, we get a screen space box around it. It's a rough one, right? It's the best we can do. We actually take the view space bounding box and then move down to screen space and take the widest area, so it will always be a little bit off. And then what we do is we figure out, like, right, what nearest power of 2, so on the longest edge, which is this one, I guess, what is the nearest power of 2 rounded up, is it? And then we will have a specialized shader for rendering an ellipsoid at that size. And So what we do is so this code here goes over all the model instances and emits all the ellipsoids which pass the occlusion buffer test. And so that means we still kind of reduce the amount of overdraw with some kind of occlusion buffer. So we can discard ellipsoids which are definitely not visible right now. They're behind too many other ellipsoids. It's a rough guess again. We use the previous frame and I think we'll reproject it. So that's still got to be tuned a bit. But this code here, this visibility buffer bin emit, we actually bin to figure out which one of those perfect shaders, well, not perfect, which one of the shaders which is best to render this ellipsoid and all the other ellipsoids. We actually need to have an array to store. So this one is for all the 1x1s. This array is for all the 2x2 ellipsoids. And this array is for all the 4x4 ellipsoids. Or the ones which are at most 4x4, at most 2x2. And it's just an array. So this binning emit is just going to go over all the ellipsoids, get the screen bounding box, and atomically sort of insert them into the necessary bin. We've got 7 bins, and each slot holds the maximum number of ellipsoids that we would want to render. So we've got a limit of 1,000,000, and hopefully we don't ever render 1,000,000 because 1,000,000 is going to be quite difficult to render. But maybe for a frame, if we get into some odd state, it will do it. But the rest of the time, it should be quite stable. And especially for this game that I want to build, I don't think we have that many sort of jarring camera angle moves. So the occlusion buffer should be quite good for with a basic like reprojection and stuff. So we will probably end up rendering about 100,000 maybe. I don't know. We'll see how the art style goes for the game. But that's what I'm trying to sort of like. This is what I'm trying to get done now. Is like, what's that theoretical max that we want to aim for? Like, what are the numbers, the hard numbers, and then we can fit everything else around that. So after we've got them binned, we can then initialize the visibility buffer. So right now the visibility buffer is literally a buffer. You hear the word buffer for like depth buffer, Z buffer, and G buffer, right? But they end up being textures. This would be a texture, but we have a problem where on Vulkan, atomic operations with a 64-bit integer is an extension, and it's not really that. It's not as widely supported as 64-bit atomics into a buffer. So I think it's around. I think there's twice as much support for it to be into a buffer. So I ran some tests. The performance is basically the same as if I was doing it into a texture anyway. At half the resolution, half the pixel size as well, it's a bit confusing. There's probably some ways we can optimize it a bit further. I can go to the shader code right now. Yeah, so we just initialized the visibility buffer to infinity in the high bits, and that's where the depth is stored. So we put infinity in those high bits, then a max U32 for the ellipsoid index. And then we call this sort of like render setup. What does the render setup do? Oh yeah, it just sets up all the indirect arguments for all of the ellipsoids that we've binned. Right, so we've got like 7 of these visibility buffer render args. They're the 7 bins, right? The 1x1, the 2x2, 4x4s, 8x8s, up to 32. And the last one is 32 plus. So it's everything bigger than 32. And these are all the specialized shaders that do that. All they do is, they've got the box around it and shade all the pixels for the box. So for this one, it's just in a 1x1. So each thread in the thread groups grabs an ellipsoid and just renders the single pixel, or tries to render it at least. And then if it fails, it returns. If not, it does the atomic min by packing the depth in the high bits and then the ellipsoid index in the low bits. We might be able to change it a little bit more in the future and put some extra stuff in there. And then we do the atomic min, and because the depth is in the high bits, the thing which is the closest will be the thing which renders. Now, hopefully, oh yeah, and if there is some, 32 bits is a lot for depth, so it should be fine. But if there's some collision, two things have the same depth, then obviously that would just get bits, and that would get minned, or the minimum ellipsoid index will obviously just win. So that's all it'll be. So yeah, that's basically it for the renderer. Because then, now after we've done that render setup, we get all of our shaders, and we go over all the bins, and we dispatch and say, render a 1x1 squared, 2x2 squared, and hopefully there's no barrier between these, so they'll all run at the same time, and they'll just, basically rasterize. Well, they kind of ray trace, but it's like a little quad perp on the screen around the object, and it will atomic min it and try and render it to the screen. So there will be some overdraw, right, overlapping ellipsoids and things that are right to the screen, but that will hopefully be minimized because we've got the occlusion buffer. And then we've got this debug shader that, because we ended up using a buffer in the end, it just basically takes the buffer and turns it into two textures, the depth. It just puts it into the depth texture and then puts it into the ellipsoid indices texture so we can debug it. But this will not have to be used in release. It's just there for this time here when we're developing it. So the next thing we'll need to do is actually shade. Visibility buffer shade. So this will basically take after having all of the overdraw happen in a very sort of cheap way, we then take the final result and we run the material shading across the full screen and shade, just shade every pixel, with all of the PBR lighting and stuff like that. So that'll be kept to, it's only one time per pixel basically that has an ellipsoid on it. So we're going to take in the visibility buffer as read only. We're then going to take in the we'll then take in the scene. So there's an output texture, right? That'd be the scene divs. I'm talking about the scene texture. And we'll probably use the global res maybe. Yeah, we are as read only because we get access to the right. We currently store the irradiance map and the environment map and the pre-fill map in some globals. Yeah, I've got to sort that out. Maybe we'll make this static in the future. No, it's just static integers we compile into the shader or something. But yeah, so we have to sync on those explicitly, so sort that out. So visibility buffer shade. Right. So we dispatch that full screen and jobs are good. And so let's find the debug one and we'll copy paste that and write a quick shade. Probably wasn't a good idea. Okay, so do the Morton swizzle such that every fourth reds is in a 2x2 organization. We take the pixel out of the visibility buffer, depth, and ellipsoid. We actually need the ellipsoids in there as well. I did forget about that. We can put that in. Oh. So read only, the output is going to be on currently it's 888. We still need to do HDR texture. But there we go. And then what's the other thing, eh? We also want to output, maybe we should output to the depth buffer at this point. Yeah, I think we should actually depth buffer. Hey Lupo, biggest was the first million to read about that. Right. 9 or 10. Yeah, I don't know who was the first billionaire I learned about. Maybe it was Bill Gates. But yeah, monies, lots of monies. And he goes and buys up all that farmland and, tells people what they should be eating. Or whatever. First he tells us 64k ought to be good enough. Then he tries to tell us we can't eat meat. Bill Gates. Yeah. He also was good friends with Epstein as well. Just remember that. I wonder what else. Oh yeah, well, we wanted the ellipsoid, the actual render ellipsoids. We don't need the screen bounds. That's right. So we'll put the depth buffer in there as well. Depth texture, I called it. Right, to break the oh my days. And there's the ellipsoids. In you go. All right. Back then, didn't know any English. Also, post-Soviet period. Most of the Western things sounded amazing. Right. Interesting. Yeah. That's what, like, over here, people have this fascination with, like, Japan and stuff. Because it's just so different. Excellent. Alright, so here we go. Do a bit of shading. So we get out the pixel, we extract out the depth and the final ellipsoid. Now, if the ellipsoid happens to be a yeah, so if it is the U32 Max one, then all we want to do is shade with the cube map, the environment map. Yeah, sample cube, something like this. And that'll be the final color that we output. So where's the ray direction? Oh, so we need to get the ray direction for the pixels, isn't it? Yeah, we can do that. World space, eh? And we'll probably need a ray origin as well. So with the visibility buffer, we can basically reconstruct all the things we need, like the surface hit position, because all you need is the origin of the ray with the direction, which we can reconstruct per pixel, and the depth that you hit at. And then you can reconstruct the surface normal with the ellipsoid information, so you have the ellipsoid index, and then you can do all the shading that you need to do. Although I'll tell you this, some of the translations of movies were much better sounding in Russian, okay? It's a strange feeling to hear in two different languages because your emotions are slightly different, right? Yeah, like voice actors and things, and also how well you know a language, right? So that gave the environment color. And then that'll be the color. So you'd store out the depth, texture, and then you store out the color. So when it comes to one of those ray tracers, they do something like this. So like a final color. Oh, I'm talking about. Nice. And then the other case is if you get a hit. So you're more likely to get a hit. So I guess we'll say not equal. And that will go to there. So this is where we do the actual material shading. So if we find... Is it called calculate surface color? Yeah. Right, so we find one of these. It's just basically this. Plop that in there. And then final color equal c.x, c.y, c.z, 1. So what we're doing is we're setting up the shading structure, put the view direction in, so the vector from the surface that points towards the camera. We've got the hit position, so we've got to calculate that. It's quite easy though. So that is adding from the ray origin in world space with a scaled vector, which is the ray direction in world space, with the depth of the ellipsoid that we've sampled from the visibility buffer. And then the normal. So this is where we need to construct. So after you have the hit position in world space, we can then reconstruct the this is it. This is the code we need. So yeah, but we can optimize this in the future. I have to keep inversing this matrix sometimes, and it's just, I don't know what to do about it yet. So future Henry should know. But yeah, so we need to get the local space one to put into local space of the ellipsoid, which we haven't got the ellipsoid out yet actually, so we'll fish that out. So is it called the render ellipsoid? What's it called? Yeah, so that'll be BC ellipsoids, ellipsoid index. Gotcha. And then we, yeah, use this ray versus ellipsoid normal, so we get the normal for a unit ellipsoid. And then we do this adjugate matrix thing to transform it back into world space correctly, renormalize it. There's our normal. With all that stuff out of the way, we will have the two things we need, which is the hit position and the normal, and then we can shade, do our lovely PBR shading, and then get the final color out. So the material is currently global, but that actually will come from an array of materials. Inside the render ellipsoid, there is a material index that we will eventually pass that in there. And then get the final color and throw that to the screen. So that's the new shade shader, right? Although made for originally. So the next thing to do is to put a bit of a, this is render opaque, and then we'll render transparent now. But then the transparent one currently renders the opaque ones as well. So yeah, we need to, we'll put a bit of a thing we can toggle so you can switch between that and debug it. Also, Soviet culture was very, oh, okay. Yeah, okay. So what was very doing because they omit swear words, add or subtract certain words so it would sound with more meaning. Of course, not every movie like that, but big ones for sure. Okay. Right, because your language would be have more resolution in those areas or something. So you could use a better word. Yeah, I watched plenty of the Jackie Chan movies growing up. Yeah. Arnold Schwarzenegger too, yeah. Jean-Claude Van Damme. Who's that guy again? Sounds familiar. Right, what's he been in? No, I think these are a little bit before I was born. I was born in 95. Name that sounds familiar though. Okay. So what are we gonna do? So these new functions now. So we see render models. Got to change this. So the first one is emit ellipsoids. That's what we do first. Now we have two functions, say render opaques. Render opaque. I should really pluralize that, you know. And then render transparents. All right. So the thing is currently, so this visibility buffer shade is going to actually take it's going to take, well, it's going to write out the sky, right? And then this transparent one is also going to write out the sky. Yeah, you know, we'll put a, we need to put it on a toggle of some kind. All right, currently we'll just comment it out. Let's just try and get the render opaques working, the new visibility buffer. So what we need to do is make it such that the models is only missing one, such that we can just debug one ellipsoid and get it working fully. So let's do that now. So this should be rendering using the, well, I would say it would be rendering, but I ain't got anything on the screen. So what's interesting is we don't have any ellipsoids shown up here. There's also no thing saying render ellipsoids. I usually omit that from a compute shader. So render ellipsoids count. Oh, okay, so we do it here. Interesting. So let's move that now to the visibility buffer. Yeah, I think we're gonna have two of the. We might have to have two different ones because one's going to be an opaque. We might have to have an opaque array and a transparent array, so that they can both deal with those. So yeah, we've got none right now. Oh, there it is. It works. Look at that, it's rendering. So this is rendering and shading using the visibility buffer. Now my camera controls are like super interesting. Right, so we take a look at this. See, we haven't got any anti-aliasing anymore. I've buggered that up because we're using this, but right, so we've got this new sort of like render opaque. The shade is taking 0.2 ms. Apparently let's pause this, as in jitter everywhere. 32 squared plus. And as you can tell, this one is on here, we've got 1. So that's obviously the one where it's bigger than 32 pixels. So those render fine by the looks of it. We're not seeing anything cut off clearly. But we'll have a bit of a play around and see. I mean, I was one with Soviet fell, but the minimum was continue for a decade, right? Was Steve Ballmer richer than Bill Gates? I didn't know that. What does Steve Ballmer do these days? When did I get my first computer? So we always had a computer, like since I was young. When I was like 4 or 3, I remember playing like a F-22 fighter, like a plane fighting game, like a 3D one, an old school one, in like 98, maybe 99. So I played that on my dad's PC with him, and then what else? So from then we always had a really like a family computer where I play like all sorts of games, like RTSs and things and stuff. Tons of PC games, like Roller Coaster Tycoon and Guild Wars 2, RuneScape. Yeah. Like, Zoo Tycoon, all the good PC games. I used to play those. And then when I was maybe a teenager, I got my own laptop through school. And then I got another laptop later on when I was a bit older, and also built a PC around that time as well. When I was about 16, built my own PC. At first, I was doing it so cheap, I ran out of a case, and then eventually got a case for it. Good times. Living young. Right, so as we zoom out, so we currently spin in the 32 by 32 plus. We'll get to the 32 by 32 one in a bit. So if we zoom out, well, that one will change. There you go. Good. So that one's busted. You can tell. Look at that. It's just cut off. So we're in this bin, which is the 32 by 32. We see it's now running this one and this one here, 32 squared. So it's not quite big enough for some reason. I don't know why. If I hop open the viewer, no, it's just cut. Not nice. So we'll figure out why that is. I've obviously done me a silly. So, alright. It's obviously in the right bin 5, because it gets the ellipsoid and tries to render it. We We have 1024 threads, which we do a good old swizzle. So 32 by 32, yeah, gets you 32 by 32, right? So we're sort of like min bounds, and we. So the thing is like, is this thing actually? So let's print out GPU hprintf, and I should really do this if this is the first. So .x equals 0, because if not, just print out tons and tons of things. Good old GPU. And we're going to print out the range here, or the bounding box. Right, so min point x, min point y, max point x, max point y, yeah? And then now we can see, like, is that thing actually 32 by 32? Should it actually be in the bigger one? You know, see how it got in here. So we zoom out a bit, so where it doesn't work, and there you go. Now what we're seeing is some numbers, and if you do some quick maths, there's the x coordinate, and here's the other x coordinate. That's definitely double more than 32, isn't it? So there's something going on with the way we're binning it. It's binning it into the wrong bucket too early or late, whichever way around you want to take it. Yeah, it did take ages to boot up. Yes, they're spinning hard drives, man. It takes so long, especially with Windows. And then like they'll make these noises as well. Then you have to run the defragger on it just to hope you get some 10 seconds of savings or whatever it was. Horrendous. Yeah, as soon as SSDs came into play, man, PCs got like, finally we can, you know, do some good stuff on computers, as in like use the computer in a way where you didn't feel like you had to wait for it all the time, because those hard drives were just so damn slow. They're a big bottleneck for a long time. But yeah, the power of computers definitely got way better before then. Yeah, computers these days are wicked quick. They still take ages to do stuff for some reason. Right, so I think we've been this wrong one, so let's go ahead and take this with us, and let's find the thing which does the binning. Binimit. So it's this guy here. Takes the largest dimension, does it wrong. So clearly I did some maths wrong. So we're trying to get the right bin here. So let's get the calculator open and do some maths. So we had like something along the range of like 60 odd, I think it was, but let's put 50 in here, yeah? So we're trying to say we get the most significant bit. That's bit 5, right? Bit 5. So if we take bit 5. Why am I maxing it with 1, by the way? Oh yeah, because I get, yeah, okay, of course. Because 0 would be invalid. But so bit 5 is here. So if I did a 1 shift left 5. Oh yeah, of course, sorry, right, so you get 32, alright. So you should use the 32. That's the 32 bin. That's what you want, isn't it? Oh no, it isn't. Is it off by 1? Hang on a minute, why have I got... Okay. W1, 2. Oh, I've got to add 1, isn't it? Yeah, it's off by 1. Got to do the other one. Have I? No, 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 no. Yeah, 5 is the 6th. Oh no, it was 50, wasn't it? Right. Yeah, I put 50 here. And it got me this one. Okay. Yeah, so that definitely needs to be rounded up. So, right, I've got to be careful here. Okay, what does that return? So, if it's 0, then all bits in the return value be set. Okay, excellent. That's good. So, what this means we can do then is not have to max it with 1 and then add 1 afterwards, because we need to add 1 anyway. So if it's 0, then it still would go... Oh, no, 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 no. I wonder. Do we need to do a max? So what do we do for the other ones, the other bins? We have to take 1. No, it's a slightly different problem. Yeah, different RPMs as well. Yeah, true, true. To be able to drink at 5 p.m. over there. What do you mean by drink? Well, as in go for like a beer or something. Depends on the person. Some people go down the pub, after the day at work sometimes. Depends on the people. But yeah, we're not all alcoholics. When I was younger, I used to go to the pub sometimes twice in a month. That's about it. Just a way to socialize, Play some pool. Sometimes you'd be terrible at pool, and you get more drunk, and you get good at pool. Other times you're doing really good at pool, and then you get drunk and you do terrible at pool. It's just the way of how pool works. Right, so we put in 50 and it kind of rounded it down, didn't it? To the nearest power of 2. So then we just need to add 1. And that will get you in the right bin. So if you were, say, if I had 31, for instance, that'd be in bin... Yeah, give me bin 4, then I add 1, gives me bin 5, so that's the 32 by 32 one, yeah. But if I did 32, that actually gets me bin... yeah. So I need to take 1. Okay, so let's run the logic. So if you have 32, yeah, the most significant bit index, that's 5. Sorry, you got take 32, you take it by 1. Then take the most significant bit index, that's bin 4. Then add 1. And then that's your bin index, that bit in the 32 by 32 bin. Good. Now, the other logic is like, well, what happens if you get 1? So 1 will get you, you take 1 away, gives you 0. You do this most significant bit index, it gets you -1, so all the bits are on. Then you add 1, it gets you 0. That's what you want. Cool, it's looking good. So I think that's the correction. So we should be binned into the right bin that renders the ellipsoid at a specific size. So here's our ellipsoid. Right, let's just get away from it here. So here's our binned renders. So this one is for 32 times 32 plus. So it's everything bigger than 32 squared, right? Surprise to my wife. Asking how dinner went. For the boy and everything. What do we do? Then we practice walking. Because he's not wanting to walk by himself. He's a bit stubborn. He doesn't have the interest to walk, and is about 1.5 years now. Nearly. So I'm starting to play some games with him where I get him to walk by sort of playing his shows on my phone, and then I'll sort of like put it on a different chair and he sort of goes over to the next chair. So we play some good games now. We're doing this every day until he starts walking now. It's going to be fun. Right, so let's do the zooming out. Yeah, Paul. As in, you know, Reds. What was it? Yeah, we just got the Red Balls in it. I think. Oh no. You know, I forget. Piping English tea. I don't know. Well, I'm not a tea drinker. I drink like peppermint tea. I'm not a typical English tea guy. Yeah, Paul's good because you can like do like spins and stuff. It's a lot of fun. And when you just have one of those days when you're just sort of like seeing where the ball will go, and it's good fun. You know, because when you see where the ball will go, you don't even have to take long. It just goes. It's awesome. Good fun. Awesome. Have you got any pool clubs near you? Right, zoom out a bit more and see what bins they go into. So we're in the 32 by 32 plus bin. Let's get to the 32 by 32 bin, which is just the next one down. And we're there, finally. That is 32 by 32 pixels and less. And if we hop open the texture viewer, we'll go into the scene texture, we'll zoom in there. Look at that. So yeah, we haven't got anti-aliasing yet. I've got some ideas for this. I've got actually some of my own little ideas on how to do a bit of a custom anti-aliasing system. I was looking at the current solutions you can do for a sort of a pre-rastered image and doing post-AA, and I didn't really have any good solutions available. But I've got some ideas. You know, I don't want to do anything temporal. I'm not a fan of temporal. But it's all about like edge detection and these things like that. And I've got some ideas to do. And I would like to give that a go, hopefully next stream. And if it's any good, I'll post about it on Twitter and that's about it. I'm not bothered doing any of these papers where we go, in our method, this and this and this. I cannot be bothered to do any of that crap. And we'll see if anyone has any interesting ideas to make it better. But yeah. So anti-aliasing will come later. So let's carry on with this view. Oh, well, okay, maybe not. Yeah, let's carry on with this view and zoom out even more. So in the bottom left, we've got visibility bin counts. We're on 5 right now. We're looking to get down to the 4th bucket, which would be 16 by 16 pixels. All right, we're there now. So there's no jump there in quality at all when we go between the two bins because it's just putting a box around it and rendering the pixels. That's all it's doing. Maybe we can have more bins and this would help with performance maybe later on. So now we're trying to get to the 4x4. It's already getting kind of small. We might be able to get rid of some of these bins and add more intermediate bins and just say, you know what, don't try and render these things because they're so damn small. Look at that. Yeah, it's already kind of a bit jumpy, isn't it? Alright, there we go. We're in the 4x4 bin now. That's alright. It's just obviously looking a bit jumpy because, you know, pixels and stuff. But let's go even smaller to a 2x2. So we honest... Wait a minute, is that 4x4? That's an 8x8. Yeah, that's an 8x8 box around it. Okay. So as I was saying, the box is a bit bigger than the actual ellipsoid. So what we might end up doing is getting rid of... Yeah, we could probably get rid of the first 3, add more granular bins in between, and that could work out well. Because we ain't really going to get anything. I'll keep trying to zoom out. Oh. Okay, I think it got so small that it just got... Alright. I think it got discarded with the shader. What was it? Sorry, not the shader. What am I talking about? When we do the occlusion culling pass, there's like a minimum size or whatever. I made it smaller than a pixel though. Interesting. Right, we're going to start printing out the box now. No, we're not using LEDs. I don't think we'll need LEDs for this game, to be honest. I don't get pubs or bars, but same to hear people drink, play ball. Awesome. Yeah, there will be plenty of non-bar pool clubs. Right, okay. No, I don't think that's the thing here. Or maybe it is. Right, so yeah, I'm a little bit confused with that. So we'll try. So I'm going to print out the box now, you know, actually see what's going on. Let's gradually zoom out. Eventually it just disappears. And it doesn't even get binned into anything, so it's interesting. Right, so in the 32 by 32 bin at the moment. In the lower left, it's in visibility bin ellipsoid counts 5. Now it's in 4. That's 16 by 16. Now we're in the 8 by 8 finally. Yeah. Say it in it. Hang on a minute. 957. Yeah, that's 8. And then Isn't that 9? Yeah, how's that in that one? Five, 3, 7, and 5, 6, 4, 6 is 9 difference, right? So it shouldn't be in that bin yet. But maybe because they're integers and they're actually like I rounded down, won't it? Yeah, so really, okay. It's probably because like these both rounded down rather than taking the difference first and then. Right, I don't know. Wouldn't it be better if these rounded to a pixel though? Maybe something we should do is when we get the ellipsoid bounds, we should actually round them to a pixel. Yeah, we should probably always round them to a pixel. We're gonna have to do the crappiest thing though, mind you. And that'll be sill and floor. Did I do that the wrong way around? Of course I did. So you floor them in, sealing the max. Right, so that'll be better. So that should yield better result. It's going to be a bit slower probably because there's an extra pixel border typically. But when it comes to sort of, but now we know those floating point numbers will produce whole integers basically and not do silly stuff. Well, basically full pixels rather than half pixels and stuff. Gotta go. Have a good rest of your day too, Lupe. Thank you, popping by. Right, so zooming out here again, and we'll eventually get to the 8x8 bin, which would be visibility bin ellipsoid counts 3, and then we can look at the size of that. And nearly there, come on. So damn small. Yeah, the problem is I'm looking at it from diagonally, so the box is actually a bit bigger than the ellipsoid is that you're rendering on the screen, you see. There we go, finally. So that one ticked, and that is 8 difference. So we see down in the lower left. Oh crap. Well, I lost that one now. There we go. So the B box, that's 8 difference, right? And then this one's 7 difference. Yeah, so because the largest dimension is 8, it finally goes into the 8x8. Because they all fit into at least 8x8. Now we make it smaller and smaller and smaller. Where does this go? If I go more on the same axis as it, yeah, render ellipsoid 0. He actually stops running the full ellipsoid. It got so small. So that wasn't the problem of the... I know now. Yeah, let's get down to the same level as it. Oh, crap. So if I get down to the same axes as it, there'll be less, the bounding box will be less. Because it's putting a screen space bounding box around a view space bounding box, so therefore it gets more stretched. Like, well, the view space bounding box is a max around the local space bounding box, so the more the bounding boxes are different, so if they're basically the same, then there'll be a lot more tighter fitting. Right, so we're getting to the same sort of level here now. Right, here we go. So there's the ellipsoid off into the distance. Crying out loud. As you can tell, my camera controls are about on point. Okay, so we're going to slowly move backwards and go down to be more aligned. And hopefully the bounding box becomes more... I don't think we're going to get to the lower bins. See, when it's this small... Okay, what's the width? That's about 6 pixels, the box. So it causes the render ellipsoids to not even be showing. See, it's so damn small. Alright, so what's the width on that? The width is about 5 pixels and then it just disappears. Alright, so let's take a look into what is changing those render ellipsoids. Count. So I think it's this one here it does it in. So this just goes over all the models and all the ellipsoids and just plops them out. So here it is. So there's like a fade out alpha. Is that the thing that's the one that's doing it, you know? It might be. I don't know if that was it though. Like what else? Oh, okay, it got so far away. This is where it is. It goes so far away that it's actually further than 256 from the camera. Interesting. So with that in mind, we know we're not going to get... So those 4x4, 2x2s and 1x1s, those realistically... No. But it all depends on the scale of the ellipsoid, doesn't it? So what we can do is change the scale down even further. Let's change it to 0.05 on the ellipsoid that we push in. And then we take a look at that one. Right there, it's so damn small. This one should be a lot easier to make smaller. Should have really lined it up a bit. Alright, there we go. On the same level, it's right there. It's so small. Let's move it down quick. That's in the 4x4 one there. You can barely see it. The way the thing has a lot of error on it. Like the way the amount we compute the box in screen space has so much error on it that it's basically 1 pixel at that point. You know? Yeah, there it is. It's basically 1 pixel. What can I do about this? Can I? There we go. That's a 2x2. with a 1x1, 2x2, 4x4, with a 4x4 to try and render it. It's about 1 pixel. Okay, so I don't know if we want to be rendering stuff that small, honestly. So maybe what we can do then is we can take so those visibility, what we call render args, render shaders. Yeah, so maybe the minimum we'll probably support is 4x4. We could offer more granularity here. You know, I don't know, like, or do you offer like a 12 squared? The problem with that is, well, what is 12 squared? Does that get you a good number? Right, it's not divisible by 32, which is the wave size. What is divisible by 32? That's a good question. So, well, there'll be no squared number. Yeah, I guess it's only the 8/16s in that which be divisible. You get a little bit of waste. So that was 4.5, so you got half a wave of waste, which is probably okay. They'll probably return early anyway. So we could do like a 12 squared one if we wanted to, or a 24 squared one as well. And that can save, how many waves can that save? Well, wait, what would it save? So they'll dispatch, they will try to run, realize they're off the edge of the screen. Yeah. So 24 squares gets you 576, whereas 32 squared gets you 1024, isn't it? So how many 32s is that's obviously 32 32s, whereas 24 squared is 18 32s. Yeah, interesting. Maybe we'll have more granular bins. So we get rid of these two. But then to calculate the way, yeah, so for now we'll just use these bins and get rid of the other shaders. So we take the bins count, drop it by 2, and we shall clamp this in between 2. So we want to have like a bins power of 2 min power of 2 max. Which is 6. And then the number of bins is take. So we're at 5 bins now, right? So it's let's take that which is 4, then plus 1, because it's inclusive. So then that would be a power of 2 min power of 2 max. I think that's right. Let's double check it. So once you've left 6 is 64, right? So basically anything after 32, 32 squared, it uses this one. Yep. And then 2 is 4x4. So we do that there at min max. So that's good. So 6 take 2 is 4 plus the 1. That's 5 bins. Right. Good. That's all good. Cool. So that should be everything working now. All we have to do... Oh, crap. My compiler doesn't handle constants that need calculating. It unfortunately wants you to... Alright, that's okay. I'll live with that. I should pre-process, evaluate that or something, but anyway. Oh, it's not binning at all? Oh crap, we've got to take 2. We need to take 2 at the end. Oh, wrong one. Right, so we took a 2 such that it would be aligned properly into that visibility, but pins array. There we go. Okay, so that's good. And as we get further away, it will gradually go down. So now we've got this working. Why don't we start doing some performance testing and just see how well this visibility buffer performs in comparison to that sort of renderer which also supports transparency. And then we will... Right, it seems to be rendering okay still. You see, yeah, we'll probably make them fade out when they get small enough because it's just pointless trying to render these things. You know, maybe when they get small enough, we'll just make them transparent. What's the height of that? That's an 8 bin, isn't it? Yeah, actually, we're going to do 8 by 8 as minimum, maybe. Because it's just so damn small. You should probably start fading those out at this point. Or maybe when they reach 4, you start fading them out. Yeah, it's so far back. Okay. Right, maybe we drop another bin. Yeah, let's just drop another bin. Let's render that one. Hey there, Black Knight. Any thoughts on computer shader engines in browser with WebGPU? Seems like a good delivery platform. You know, if I wrote a specific renderer for every platform, then I could probably do that. The problem is WebGPU doesn't support... Oh, for crying out loud, I got the wrong one. WebGPU doesn't support... How did that work? How doesn't that do it? I took away... Three, 4, 5, and 6. Yeah, it's 4 of them. Oh, weird. I didn't... Okay. And didn't change the shader I launched with. Yeah, so basically, my only criticism with WebGPU is it doesn't really support bindless. It doesn't support bindless, so I can't use it personally. I can't target it because I've got my own shader compiler and GPU API. Yeah, it's just not possible to target it for me. But if I wrote a specific renderer for a target platform that I want to target, or you didn't use bindless, then it would be a viable platform. You know, getting your games on the web is good if you're an indie, I guess, because you can just deliver it very easily, right? the downside is, okay, I want to comment out those those other shaders that we got rid of now. You know, or if you're trying to do, you know, if you're a big company and you're trying to do some sort of like free to play type game, which is got some web payments in it, right? And you can sort of buy stuff and you're always online, then yeah, it's a great delivery method because no one has to install anything and they can just play the latest copy of your game and, you know, play at somewhat comparable performance to a desktop version, but also maybe they can download a desktop version if they want slightly better performance, right? But yeah, it all depends on the type of game you're making, that is for sure. Yeah, I think it's going to go into those bins okay. So this means then we can do the performance testing now. And we'll switch between two based on a setting. What settings have we got? Let's see, listing occlusion call and occlusion call debug. Right, we'll take that occlusion call debug and we'll use that as the option because we're not using it right now. And we'll use it to toggle. Oh, they're still rendering fine. The minimum is 8x8, and then after 8x8, it should start. So around 4x4, it should start fading out, and it'll be used in the transparent renderer, maybe. I think we'll see. Yeah, good point. Was that PGC talking to someone looking at platform for web to handle things like payments? Some interesting stuff happening in that space. Let's wait and see. Well, there's plenty of stuff, right? There's like Stripe and things and whatnot, right? You know, you just have, when you talk to your server, it goes through like some payment provider and, you know, it's just a case of doing that legwork. So what's next, eh? So let's go into the graphics. I'm going to go ahead and, so we've got the single render opaques. Hopefully this will be the preferred renderer. So we're going to test it out. So user if G settings, graphics, occlusion culling debug equals 0, else renders using the transparency one. So this one supports transparency, but it also renders opaques as well. But I'm hoping that we can just use this new opaque renderer and it'll be much better. And just use the other one for rendering transparency because it's really good at doing that. You can overlap ellipsoids and spin them around, and there's no sort of like Z fighting at all. So it's cool. And I'm just trying to see like what's the sort of best method. Nice. So let the fun begin. So we're going to go to the models, count, and what do we have? It was 25 on it and then 4. So that emits like 1,000,000 ellipsoids. So there's a 4x4 model of ellipsoids, and that is model instance. Now, clearly somebody forgot to leave a print statement off in shader code, so it just went completely bonkers and crazy. So let's go ahead and get rid of that. The next thing is, there seems to be far too many things rendering, or a bug in which it is causing, look at that, it doesn't even render. But if I switch to the other one, it renders fine. It should render this sort of wall of ellipsoids here. This one doesn't. But we saw it render fine, right? So what is, for crying out loud? Okay. If we bring this down a bit, what's the problem, right? Okay, you can render 1 fine. You do 8. It's like, no. You do a 2x2. Apparently it's like a big no as well. It seems to be the multiple instances being a problem. I have no idea why. They can't all be overwriting the same one, can they? It's an interesting thing, isn't it? So why don't we plop this back to something small again. And I'm going to go ahead and find... it's this code here, the bin emit. So in bin emit, we want to know, like... So it's getting all of the... going over all the ellipsoids. Getting their bounding box. Then for all the 256 threads, is trying to basically, in a performant way, increment this number atomically and figure out the right insert indices. Or there's, a bunch of bins. That's the problem. Oh no, it isn't the problem. Right, we're in the right bin index. Yeah. Bins count is 4, that's fine. So there's something to do with like... Yeah, something we're going on. So we're going to say, okay, GPU hprintf. I'm going to print out some ellipsoid index. We're then going to print out bin this, and then at this index here, yeah? So ellipsoid index. Maybe I could do this instead rather than doing all this cryptic stuff. So ellipsoid index, bin, insert index. So bin index, insert index. So yeah, the insert index is going to be into the big old buffer. So it's in strides of 1,000,000. Let's name it for web games. Oh, right, I see. So, like a store, right? Yeah, I don't know if you can do that. Maybe you can. But people can just download the binary, right? And then you have to have DRM and all that. I don't know. Alright, so it's up this. This is got 2x2 now. 2x2x2. So there's 8 of them. So they all go into this bin here, bin 2, which is actually like the bin which is good at rendering 32x32 ellipsoids. And they're the ellipsoid indices. The insert indices are 2, 3, 4, 5, 6, 7, 8, 9. So this is saying we're trying to... we got 8 of them actually in there. This is saying we've inserted them here. So they should be rendering. But they're not. We're only rendering 1 of them. So my next suspicion is that we're not launching enough threads. So we take that print statement here and we go to the one where it's trying to render in. It was that 32. Right, so we saw this print out in the terminal. So we saw that correctly. And if we go down to here, this these guys. So for the bin, we just put the bin ellipsoids count in there. So that was 8. Seems sensible. And it's not working. So if we find... $32 squared, it was this guy. So we should be fishing this out here. Bin offset. Oh, bin 5, you bugger. I honestly don't know why the first one worked. It's not bin 5 anymore. Right. So this is not bin 0. Yeah, I don't know how this thing rendered the first time. Bin 1. Oh no, because they had index 0 in there, so it rendered the first one. Okay. Classic. Bin 2. Bin 3. Which is the 4th bin. Alright, so where's those prints? Don't need them anymore. Alright, we're looking good. So the other one was the render ellipsoids count. I had that. I took it from here, I think. Cool. So let's compare the renderers again. Oh, I should have upped the... Oh, okay, let's test it just by scaling it with the UI. And then we'll test the performance between the visibility buffer and the tile binner approach. So 4x... Perfect, look at that. Oh. Damn it. Are we getting some errors here? That might be to do with the occlusion buffer or something like that. Oh no, it's over 1 million, is it? Oh no, it's not over 1 million, it's 100,000. Go plenty more than that. So if I pause that there, we can then also reach over to... So currently I've got the renderer switching out here, so this is the tile binner one, this is the visibility buffer one, so it's still got a bug in it. It's kind of dancing around a little bit. You know, we're at 50 or 1,000 of them. So what's interesting is this one renders 300,000. But then this one only reports 57,000. So where's the discrepancy there? Because they both run the same code to tell you the render ellipsoids count. So it actually emits into the render ellipsoids buffer. So So both run the same code. It's this one here, the emit ellipsoids. They look over the occlusion buffer. So I'm thinking that the depth buffer is... Let's get rid of that. Alright, let's go full screen, go full ham. Right, this one doesn't have the problem. Yeah, it's in the opaque render as well. I reckon it's something to do with... If we move fast, that's going to fail because that's the occlusion buffer just being... Right. So we look at the depth. And if I turn off occlusion... Hang on a minute. That renders fine. So we can actually compare the depth buffer. Yeah. How did this ever work? Yeah, this is zip index 0, that's how it worked. So we swap over to the other one. Oh, what have I done? I busted my thing. No, my controls. So I have keyboard controls in this UI and sometimes it gets a little bit, but oh, it's the Alt keys held down, damn it. The Alt key state is okay. Cool. So let's get this one up here. This will allow us to toggle between... Oh no. Okay, this will allow us to toggle between the tiled renderer and the visibility buffer renderer. So if we bring up the texture viewer, this is the depth texture. Now let's press left and right, and we're toggling between the two, and I'm not seeing any problem here with the depth. They both seem the same. Oh crap. Of course. This one's not rendering a depth texture out because I commented it out, didn't I? Alright, don't mind me. So I commented out in the ellipsoid ray tracer the RTAA one. I commented out at the end. It's got a lovely do not comment this. The depth texture store. So it wasn't storing the depth out, meaning that they probably both had the same bug for some reason, but I don't know how. Because it was working fine before. Alright, so this should be the opaque renderer, so the visibility buffer one. Now let's switch over to... Again, the tiled one it has a problem with. Strange. The tiled one is a 35,000 ellipsoids, and this one is about 6. Yeah, it does a lot. Okay, so open up the depth texture again. I'm going to compare. So there it is with the shade. And there it is here with the ray tracer approach. Okay, so if we take the... Go to different setting. I'm scared to press the escape button, damn it. Let's turn off the occlusion culling. I need to take off that escape key which traps the mouse. It just messes up with stuff. Probably fix that off stream because it's just annoying. But, so we've not got the occlusion culling on now. Let's find a position where it was being a pain. Yeah, there it is a pain right there. I'm seeing the numbers go a bit crazy. Okay, so we bring this one up. Now we're going to look at the depth buffer and see. So this is the one, the shade one, it looks fine. Yeah, they both look basically the same. What the crap is going on? Huh. I have no idea. So why is it failing the occlusion culling the next frame. When we have... There must be something we're not writing out to, or... something else a little bit weird going on. Right, so I'm definitely not using that anywhere else. Copy depth to occlusion buffer. Right, so at the end, got to read write on the depth texture, so it's definitely writing it out, right? So yeah, if we go to that copy depth, then it copies it to the occlusion texture, right? It always copies it. So if we take a look at that, we can see if there's a bug in that copy. Yeah, so it's off right now. So we go to the occlusion texture. Right. That's interesting. That should be okay, right? Yeah, so the left is, so off would mean the opaque renderer. That seems alright. It's copying that okay. There's nothing odd there. And nothing odd here either. Damn it. Why? Change the white black levels, but so is it getting downsampled? It might not be because it's off. But yeah, I think right, but if we turn it on, we might see yeah, so it's not getting downsampled anymore because we turned it off. So we'll get cleared. But I reckon there might be like a hole. And that hole... No, there can't be a hole. Right, so what's going on in transparency, which is not going on in the opaque render? So it sets up the bins and does the ray tracer. Renders out to the scene texture and the depth. There's nothing there that seems different. The end and the visibility buffer, it does the same thing. And then we always run the same code here, which does the binning. Sorry, does the occlusion culling of the objects. So we'll get the bounds. You see, I reckon... Right, so what can we do? So we can get it to take the depth, copy it, downsample. Let's make sure they all pass the occlusion test. Right. And then let's see in action now. It's going to be more expensive. But we should maybe see a... Do we still see a flicker maybe? There's no problems here rendering at the moment. Let's pause and take a look at the occlusion texture, but then... And then downsample. But it didn't happen when it was big, that was the thing. There's not really like a hole in it later on, is there? The hole will be fine though, because it means it'll pass the occlusion test. So... Man, what could be causing this? So it's... Why am I thinking it's in... So like these ones at the back, like, hey, I'm not rendering, so there's only like 3,000 of them. And then if we switch to that other renderer, so hey, I want to render all these and there's 2,000 of them, although that one didn't render, that's interesting. Okay, maybe it's a different bug now. No. Yeah, so I think the reason why these render ellipsoids are changing every frame is because the occlusion buffer changes every frame, and it's just like a feedback loop that's going on. So there's something to do with the renderer. Yeah, there's a bug in the binning, in some of the binning code or something, which is causing it to not insert correctly. I would say that's it. And therefore not get rendered properly. Ooh, this would be interesting to find. Okay. So it's not any of this code. Let's find the visibility. Right, so in the bin emit, it might be something to do with this. So let's go over this shader. It's a little bit complicated, but it goes 256 ellipsoids at once in a single, not at once, in a single thread group. So there's about 8. Yeah, I guess there's 8 waves running independently of each other. So the first 8 threads within the thread group will set, oh, it's less than 8 now, isn't it? It's 4. That's right. The first 4. Alright, we'll look at that in a bit. The first 4 just clear these out to 0. Wait here for the rest of the waves to get here before carrying on. You get your ellipsoid. If you've gone outside of the ellipsoids, you return early. Now you get your bounds. You wait here for all of them to get the bounds. Why would you wait there for all of them to get the bounds? Doesn't make any sense. You get your bounds. Calculate your dimensions. Get your largest dims. Largest dimension. Find the bin. We looked at that code many times. I think it's fine because we tested it with one ellipsoid. It seems to be going in the right bin. I think it's the way it's adding them, maybe. So we then atomically add with all the other waves within this thread group into the right bin. So that will get us a relative index from within. So essentially we're finding an insert index, but this is all set to 0 initially. And we're finding our relative insert index from all of our group of threads into 4 different bins. And then this is an atomic adder index. So this is trying to figure out which of the threads are going to become atomic adders. Wait here until all of them have done this. And then if we're one of those atomic adder indices, because we could, ideally we need as many threads active as there are bins, but there could be a case where we might not. So we have to handle that. So we pull out the atomic adder index thing, and that gets us how many threads actually added in total. And then essentially we go over all of the bins, striding by the number of threads which are processing this. We've got base bin index plus the atomic adder index. We have our target bin. If anything outside the target bin range, we extract out the object counts, and finally we atomic add with a global visibility bin. Oh, I know what it is. For crying out loud. It's this. It's not even that of a code. Right. Okay, so the problem is, yeah, so just to finish this off, we basically get a bunch of base insert indices for all the different bins that were added to in this 256 threads. Wait here, and then each thread, uses its bin index from the base insert indices, adds the relative index, and gets the insert index into the array. So that's okay. The problem is afterwards, when we've binned them all into those different bins, we now get the amount of ellipsoids in each bin, and the way we're dispatching the number of threads, the number of thread groups, is all wrong now. We actually got rid of these. We're going to do an 8 by 8, 16 by 16, 32 by 32, and 32 plus. So that is 0, 1, 2, and 4. So I can't believe that, or 3, sorry. So that code, yeah, it's just really annoying how you amend the code and it looks like it's working and then it just fails when it's much higher on. How do I image load and store given that J can change in the same dispatch? So you're saying loading and storing to the same image. So typically what you need to do is if you're loading and storing to the same image, you need to ensure that threads are not writing to the same part. So if you're doing a full screen pass, unfortunately you have to store the output into a separate texture. So there's quite a few like post-processing effects that require you mutate the image that you're loading from. So in that case, you either need to take a direct copy, or you need to do the copy before you do it, or you need to. But you're better off, but you are much better off doing the operation from the original image, and then while you're copying it to the other shader, perform that operation you want to do. It'll be much better for performance that way. Then hopefully you got some more post-processing shaders that you can sort of end up copying it back to the original texture in the end type of thing. Does that answer your question, Coffee Lover? And hey, welcome. Hope you're doing good, sir. Right, so now I think we can compare performance. Ah, shoot. I spoke too soon. The maximum number of work groups is 64. Okay. Gotta be having a laugh. Load of bananas. Who made that roll up? No. Oh, right, so I've got to do it in 2 dimensions, but that's no problem. Right. Hang on a minute. So if you overflow that, so you go min 65536, and then this would be is it divide round up? Yeah, it's divide round up. Alright, so that's launch across the X and the Y. So that should hopefully be enough. I only want to do 1,000,000, right? You know, what's the problem with that? So I think that's, if I square that number, that should be plenty. There we go, plenty. And then, so what we need to do is we need to take the Y. So in order to get this right, you do SV dispatch index.y. Oh, get out of here, I'm in the wrong one. Yeah. These are our boys here. So it's plus SV dispatch group index.y times by 65536. So that's the 8 squared one. And there we go. That's all the ones there. So hopefully we can do some performance testing in a second, hopefully. Right, scale these up. No. I minned it though. Group X. Tell me more, which one? Ah, model ellipsoids and meta-ellipsoids. Oh, so I launched... Okay, that's interesting. So the emit ellipsoids, I just had... Right. I see now. I had way too many instances. That's alright. Alright, let's go back to something sensible. I can get a million, right? Models count 25 and 8, I think it was. I think that's 1,000,000. So 8 by 8 by 8 and 25 cubed. Yeah, 8 cubed ellipsoids per model instance, then 25 cubed instances. Oh, that's about 8 million. Oh, no, it ain't. Yeah, that's 8 million. Right, I think I meant to do the 4 one. 4 by 4 by 4. Maybe. Maybe it's too less now. There we go, 1 million. So this is going to be the number we're going to test, and if we look around... Yeah, that's alright, it's not glitching. Okay, this is great. So current numbers are about 7.5 milliseconds to render this. That's about 94,000. So we end up actually rendering. We need to compare that to the other one, and then also do sort of different zooms of these things and see what the performance comparisons are. Okay, awesome. Right, I'm just gonna get another drink. Then we get back, we'll do some comparisons of things and of the two renderers, and maybe we'll get time to look into if there's anything we could make better, anything that's painfully wrong that we can maybe make better. All right, be right back. Enjoy the tunes while I'm gone. Right, welcome back everybody. It's time to test performance. So, we've got the old, well, it's not that old, right? It's the one we was just using a few streams ago. The tile-based renderer. So I bin stuff into ellipsoids into screen tiles, and this new one, which is the visibility buffer, where it gets all of your ellipsoids and renders the smallest box it can around it, round its nearest power of 2, and will atomic min that into a visibility buffer, and then shade it afterwards. So we've got the profiler here. Profiler is saying this screen here gets us about, it's a bit noisy, not gonna lie, but right, let's just leave that there like that. So this is 90,000. It's in the lower left render ellipsoids count. It's 90,000 ellipsoids that we're actually rendering. There's a million which go through the renderer, and then they get occlusion cold, and some are off the screen. So this is what I end up rendering. Now we're going to open up the settings panel. We're under the occlusion cold debug thing. We'll call this mapping to switching between the two renderers. So this one is the tile binner. This one here is the. So they're actually about 20 ellipsoids difference for some reason. Maybe just. Oh, because this one anti-aliases, I think. Yeah, you can tell this one does an anti-alias, and then this one does. So there's a slight difference on the right-hand side of the image. But anywho, the transparent render is actually more persistent in this case, and renders in 7 milliseconds. Whereas this one jumps around between 7 milliseconds and about 6. Which is confusing. So this is at this specific camera angle. So, right. So let's try and go ahead and... So, let's go ahead and shrink these ellipsoids down a bit. Yeah, the occlusion buffer's got a bit of a bug in it. Ignore that. So, alright, so zoomed out a bit here. This one is... Oh, yeah, we've got some in the 32. Yeah, we've got about 100,000 of them now in the 32 by 32 shader. So this is about 4 milliseconds. But it is jumping up to 7 milliseconds, 8 milliseconds sometimes. I don't know what that is. And now this one is at 7 milliseconds. But it goes down to 5. So it's a bit noisy as well. I don't know where this noise is coming from, I'm not gonna lie. Sometimes it goes stable, sometimes a bit noisy. But when they get small enough, this one's about 3.5 milliseconds for the opaque. Tile one. That's stable there. This one's a bit noisy now. The images are looking pretty much the same. I guess it'll be different when they are actual big ellipsoids or whatever. So this one's 3.31. At its best. But I don't know why. And that's 90,000. So yeah, it's difficult to really gauge these numbers, but they're basically looking about the same in terms of performance. So I think the visibility buffer was good at rendering very small things. Sorry, not visibility buffer. Yeah, the visibility buffer approach where you sort of like put the box around it, do the atomic min. It was very good at rendering very small things, from my understanding. But when you start rendering bigger things, then it's probably just... Yeah, you're seeing it here, right? These are going into the bin, the one bin, right? So this is stuff which fits a box around it, which is 16 by 16. So this is putting it 16 by 16 pixels, but definitely smaller than that. This is putting it at around 2.3 milliseconds to render those, and this is about 4 to render all of these. About 71,000. So Yeah, so I think the smaller they get, the better the visibility buffer approach is. But then the bigger they get, the tile binner is better. I think though, right? Let's make these really big and let's see, right? So let's do this sort of look where you get a good range of them, I guess. Where you got a few big ones, you've also got like a bunch off in the distance that get small. So this kind of jumps all over the place, which is a shame. But that's about 21,000. I end up getting past the occlusion buffer. I don't know why it's so jumpy. It's hard to tell. Oh, it is. I thought if I press the arrow keys. There we go. Right, they both seem about the same. Okay. How many? So the problem we have with the tile binner is that it would emit so many objects that it would be like, for the big ones. If you see in the lower left-hand corner, this tile bin sort entries count. There's 800,000 of those, even though there's only 21,000 ellipsoids which pass and go into the. Wait, what was I saying? Yeah, there's only 21,000 that pass the occlusion test from the million that we've generated here. And also the frustum culling. So there's 800, there's 860,000 that get sorted into tiles because it has to duplicate each of these ellipsoids for every single tile that it could be binned into. Oh, it has to duplicate references to those. Just got rejected from a job after applying 7 hours ago. Oh, damn it. Yeah, the job hunt is difficult. Honestly, I just got lucky. Just prayed about it a lot, and I managed to, get an interview with someone who already kicked it off with. So, it's tough, especially these days. Looking in the games industry, real tough out there. All these layoffs that have been going on and stuff, Yeah, these are looking about the same. So I feel like I don't know where this damn noise is coming from. Because sometimes one of them is not noisy, other times the other one is noisy. Sometimes they're both noisy. Okay. Hmm. Yes, things to debug and figure out, like. Right, so what's another good test that we could do? Yeah, so maybe it's alright that we just don't do the visibility buff approach. It was interesting. So I guess the other thing we can do is tweak the visibility buffer renderer and see, you know. Well, it's only at 1080p that we're testing it. What about 4K? I guess is another approach. Yeah, we're looking at really performance for 1080p though, because this is like a mid-tier card. I want a 1080p. So I was thinking like, so I think in engines they typically target 4 milliseconds just to render out the G buffer, I think, and then they to shade it afterwards they spend like another 2 milliseconds. So I think there's like sometimes like a 6 or 8 millisecond budget to render everything shaded to the screen. So we try and aim for that. It means we've got 8 milliseconds left to do other things, right? And that's what we're going to try and figure out is like, what's the maximum number of ellipsoids that we can push through the renderer and expect to always get a good result and tune it around that way. So yeah, this one here is about 10 milliseconds. And then we flip to the other ones. This is the opaque. Yeah, and this one again is about 10, but it's more stable. And that's hang on a minute. Why is there a million? Oh, sorry, no, 100,000. I'm misreading it. Yeah, so that's pushing 100,000 through it. It's a little long. Okay. So that's kind of a good debug for you because you're getting some kind of close ones, but then they're going off into the distance in two sort of ways. And you're kind of filling up quite a lot of the screen as well. So yeah, I think maybe a million might be a bit too much. We could probably drop it to 500,000 and it might be better. Yeah, 500,000 might be more of a bearable number. So that's about 600,000. Yeah, so we could probably say 500,000 ellipsoids in the whole scene. Somehow we got to like stop it at that, and then that will probably leave us at, this is about 65,000 that end up getting pushed to the screen and being rendered to get this performance. Well, at least I won't have to write another anti-aliasing system. I was going to have to do that if I kept the other one. This one, those 5 milliseconds, damn it. So it's quicker. You bugger. This one's quicker here. But it does jump up to 7 though, every now and then. I don't know why. Maybe we'll figure out like what's all this jumping, you know. Why is it spiking like this? Is it the number of draws that are changing? Is it, you know, what could be causing such a thing? Like we just switched between this one and that one. And now it's like, right, here we go, it's better. So yeah, stable there. But it's kind of stable what it's pushing through the renderer, the visibility buffer and everything. The amount of ellipsoids they're getting is stable. So what is causing the flicker? Although the noisy results. So in this case it could just be the fact that it is the atomic min method, and it's the way they get dispatched is so random that it causes more noisy results, and therefore the other one is going to be more stable. Yeah, I think that's it. But I don't know what will cause the... Because that sometimes jumps up quite high. But that might just be it because it's fighting with OBS at that point. Sounds about 4 milliseconds. Let's switch to the other one. It's about 4 on average there, but it goes down to 2 for some reason. So there might be some approaches where you could take, well, with the sort of visibility buffer, you could... So I don't want to write it off too early, because we just gotta... So I guess let's build a slightly more realistic scene, I guess. So why do we, on the y-axis, right, at least drop let's still keep the number of ellipsoids the same, but let's drop the y down by 2 times. So compress them down such that we're more likely to get a nice long, or maybe 4 times. We'll get a nice long, well, no. Wrong one. Oh, that's the model instances. Oh yeah, that's right. I thought that was within the, within the models, the instances. That's good. So we should get a nice sort of long... Crap. So the issue is we're still emitting more ellipsoids. And they're just overlapping each other now. That's 1 million. Yeah, you know what, let's properly do it. So this y here, why don't we drop that down by 4? Or maybe more, let's do 8 times. So divided by 8 here. So now when we talk about in the UI, saying like, well, how many of these have we got? You know, I did say cube. Well, that's kind of not cube anymore. It's kind of this many. Right, that'd be better. So now I'm hoping we can just get like a nice big landscape of ellipsoids and just see it, you know. Well, that was the hope. I don't know what the crap is going on here. Right. Width. Height. G models divided by... Right, let's try that out. See what happens. There we go, we've got our floor now. So I'm thinking like this game is going to be sort of like top down like this, and right, it says 128,000. Let's keep it going a bit. Alright, we did say 1,000,000 though, didn't we? Or 500,000. Yes, do 500,000 here. So, right, let's just look down at that to some degree. Well, okay, we did 1,000,000. Then we can crop it out. Right, so there's definitely 500,000 going through there. So there's 256. I think I accidentally took a screenshot. Right. So performance there is about 18 milliseconds on that visibility buffer approach. Let's get that. Right, and this one is about 22 milliseconds. Okay, interesting. Oh no, it's about 28 milliseconds. Right, so this one here is actually way better in this case, but still a lot. So the other thing as well, right, is we're rendering with a really stupidly high field of view, which ends up making the boxes of the ellipsoids a bit too big. So I think if we're going to be measuring, so there's two things we got to sort out, right? The bounding boxes which go around the ellipsoids are actually extrude. Okay, so let's wind this back a bit. Let's go back to something more sensible. So let's undo this here. We'll get back to it. That landscape again. But let's focus on what next contributes, the next big thing that contributes to performance. And that is the fact that the more incorrect the bounding boxes around our ellipsoid, the more tiles the ellipsoids end up in, and the more extra pixels that we try to render around the ellipsoid for the visibility buffer approach, right? So if we take a look at what I mean by this, like actually see it. So we can see it here when we emit the ellipsoids. We'll get the bounds of the box. I'll simply just plot this out here. So we'll do a draw 3D, 2D, ABB min max, bounds dot min point, bounds dot max point, depth, bounds dot depth, there's depth in there as well. Border, let's say 1 pixel, half a pixel, that'd be enough. Because I think it's done in halves. And then -1 for white. So we'll see how much of a problem this box is. And when it's got a high field of view, especially when it's at the edge of the camera. Oh, come on. Where you at? Should be showing. Maybe that does have to be 1. There we go. So as you see, it's really off. When it's in the center of the screen, it's the best. Goes towards the edge of the screen, it really starts to shape and be wrong. And the reason why that is because it's in it from the view space bounding box, and obviously it's got a high field of view. So I'm wondering if there's maybe some hacky way we can compute a screen space bounding box, but you know, it's going to be completely mathematically fudged, shall we say. But we could probably get a better box, and that will help with performance a bit and really reduce the amount those things get throttled by and with. So what we're looking for is a so we get to the implementation of this. We also get the screen outer half dims in view space. Right. So if I take this as well, we can draw the view space. Oh no, hang on a minute. Don't mind me. So draw 3D, OBB, view from ellipsoid. I don't think we want, I think I can work with a normalized one. There's just some thickness in local space, I guess. 0.05. -1. Or maybe I can do a red. Z-test false. So now you get to see the view space bounding box around the ellipsoid as well. There we go. So this is why the box is wrong. Oh no, there's actually another box. Hang on a minute, there's another one. Guess what those numbers I had in here before. Sorry, that was the local space bounding box. And then we'll do a view space one. Was it in a green? So this is a ABB. In view space, a center pos. Half dims. Alright. Oh crap. Right, so now you can see the 3 bounding boxes and where the sort of loss of precision comes from. There we go. So the green one is the view space bounding box. So this view aligned. The white one fits perfectly around the view aligned bounding box. But obviously the corners, as you can tell, get lost. And then the red one is the local space one around the ellipsoid. So if that ellipsoid spins in the world, so will this red one. That's a good quote. The man with a rainfall rainbow, yeah. Nice one. So yeah, as you can tell, whenever you sort of line up perfectly with this thing, view aligned, you kind of get a perfect box, but it's still way bigger than the actual ellipsoid ends up being, right? So there's plenty of room to fudge, but when it gets small enough, kind of gets less error. And then, but as you can tell, with a high field of view, and well, we'll test it, right? We'll add a field of view option so we can change it and see that. But as you can tell, it really stretches towards the edge of the camera because the box of the view space box stretches and it's aligned to view space. And you see, I wonder if we just took the point, why am I not taking the points in local space in all of them into view space. Yeah, I think that'll be the answer, right? Take all of them into view space. And then you've got a bit more of a snug box, isn't it? Look at that, it'd be way better. If we take all the points from the local space box, because you can't optimize it and be like, this is what I've tried to do. I've tried to optimize it and say, hey, take this corner and that corner. And that's all you need to take into screen space. But I think we'll just take all of the points, because this is not the performance intensive bit. The performance intensive bit is getting boxes which are too big. So we instead take all of the points inside the local space of the object, transform those all the way to the screen. And then that would be better. It would be a snugger box. And then that view that we had before should perform much better. I wouldn't know if it's what we would hope it would be, but it would definitely be improved. And there should be less duplication and stuff as well. Yeah, it should, yeah. So where's that? This one here. Outer ABB from local. So we can just change how it works. So yeah, this is me trying to like only take the right edge and do a minimal amount of maths, but so this one gets the, yeah, this is where it creates a lot of wastage and gets the view space bounding box from the local one and kind of does some maxing and stuff. So we're going to try a bit differently. I've got to get good depth though, mind you. The depth in view space, we've got to get that still. So let's copy paste this, and this is the old one. Old one with less precision. Ah. Go quicker. Right, so the new one is to scale the points. Transform, transform, transform. And transform, transform, transform. Right, okay, so point. I think there might be ways to optimize a bit further. I think there was a blog by Arseny, wasn't there? Rust and culling optimization. Or there was a sort of a screen. That was put into screen space or something. Yeah, projected bounds. If the input ABB hang on a minute. Yeah, but again, this is rough, isn't it? But yeah, I wonder what Bmin Bmax is. View projection. Yes, this is what I was about to do, right? Then yeah, then bring it back into. Just get all your points. Right, so he's taking the half extents. and then bring those into instead of computing the corners, you multiply the world space by multiplying the world space corner of the ABB. Take advantage of the distributive property of matrix multiplication and note that right, interesting. This allows us only to compute one full vector matrix product with 3 products to reduce the row column multiplication, and the rest of the computation is just as follows. Nice. So that seems like it might be exactly the same, but with less operations. But it's not an approximation, right? Nice. Let's give this one a go. I'll drop the link if people are interested in the blog. But yeah, so if we take, so ours is local space, so it's not world space, it's local space, but it should be alright. So what we want to take is the view space extents. Yeah, so these are the bases. So take the basis vectors, bringing them into view space. Yeah, we've already got those. They're on the matrix. Yeah, so we've already got they're just the basis vectors. Okay. So basically you take the transform, the translation, and yeah, so mine's done with a point in the middle, you see. So I can compute all my, right. So I don't need to do any multipliers, basically. So I take the view from local and do a translation sub. Yeah, see that's the problem, is mine is in the middle. So I take, yeah, I've got to do an add and take away of Alright, let's figure this one out. So it's an add translation. So you got the basis vectors, right? You got the one which points down the x, the one which points down the y, and one which points down the z. But you don't know so they're just adding. Oh, but then it's doing a P4 plus Z. And Y. Ah, interesting. I see what's going on. So you're the lower left corner, then you get in the other 3 corners. And then you get the other corners by adding them on right. I see. That's pretty clever. Hey, Ilikem. What we're working on? Okay. Okay. Probably a Gen Z. Very impatient. View from local axes. Right, so that'll get the X. So we could probably sub from there. Oh. Yeah. I think it's in the center, isn't it? So if you take all of the basis vectors, add them together, that's the half extents, and that's what we can use to get back. We can use to get to each corner. Or use to get to a corner. And then you can use the basis vectors to... Because we're already in the center, we just have one of the axes. That won't get us. So I guess we'll do the min thing. Maybe. Okay. So I think we need basically that sort of like width. That sort of x vector. So I think we'll scale it by 2. So mol-s is there a better way to do it than this? You don't know if you've reorientated the box. Your basis vectors, to get to a single corner you have to at least add add 3 of them together anyway. Yeah. And then you can get to the rest of the corners. Right, so now you add... You also want to get the sort of the min position. I guess we'll call it P0. P0 is this. Take away the sum of all of your axes. So that'll be something like this. Add. Alright, I need 2 parameters. There we go. Add those 2 as an extra bracket in there. Cool. So we're adding... So this will get us our sort of diagonal across all the dimensions of the box. And that'll get us to one of the corners. So we subtract. That'll be the min. Now we've got these sort of basis vectors, x, y, z. But they're multiplied by 2. And now we'll follow this. So P1 is an add of P0 and basis vector Z. Yeah, I don't know why it's done it that way. I don't know how that W component thing works, you know. Where it's doing like a min of all of them because you're adding... Because W is 1. Yeah, it's definitely interesting. Oh no, it's in projection. Right. So they've taken into projection space. Mine's going into view space. Okay. It'll still work though. Because we've got a different function for that. So yeah, P1 will go across the X. So I'll go from the minimum, one of the minimum edges will go all the way to another edge, like that. Then from 0 across the Y we'll go to the edge above the min point, and then for the third or the fourth one here, we'll go across the Z. So that's got us on a ABB, that's got us 4 edges, the lower left, the one to the right of it, the one above it, and the one along the far. So you've still got to get to the one along the far. You can always add the X to get the one on the opposite edge of the bottom. So this means we've got all the ones at the bottom now, I think. Yes. Now at the top, we're still missing 3 more. So we've got to essentially add, so this on this Y one, this P2 one, we've got to add a Z to get the far one. We've also got to add an X to it. So an X and a Z, I guess, to get to the right hand side at the top. And then the final one, P7, which would be all 8 sides. That will meet, oh, P7, so that will be either a P6 or a P. So we can debug draw these points to test this works, because we've got code like that. We take P6 and add another X to it. So that means we just follow it around. So that'd be the one in the complete opposite corner from the min. Which we could have probably got by adding this to begin with, and then not be dependent on all those things to run. So you could call this the sort of like it's the half vec. It might be better that it's not dependent on all the other variables to be computed, so maybe we just pre-compute that as a P1. So it gets the 2 corners, min-max corners. So we up everything except for P0s. Cool. So, but realistically, the ones at the top, those could be done with a subtract from P1. So realistically, this is just a P1 subtract of XY and Z. I think that's right. Yeah. Okay, that's good. That's good. So after got your corners, we just project them back in a view space. So I could do them, but I can't be bothered. We need a near though. But so this is in view space. So to get a near Z, do we need a far? Yeah, so if we take yes, we just do a massive old min. What a function, a min with 8 things. Yeah, so we just min all of those. Oh my days. And a max. And that will get us. There's no way we could. Well, no, there might be an easier way. So if you've gone and done this right, you've produced a sort of like half deck. No, 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 no. Yeah, that's not going to get you anything. It's all because you've added. You've got to take all the Zs from all these points. I think there might be a better way. But let's do a min-max across all of them. It's going to be a bit hectic, but I think I've got some methods to make it a bit easier. If we do a min... We've got 8 points. So we get two 4x4 vectors and then do the min element of that. Then I won't have to do so many brackets everywhere. So this will be p0.x. Sorry, z. p1, p2, p3. So 4, 5, 6, 7. Good. So that's the min. Then when we see min, we do max. So max, that's far. And then near depth. Cool. So we recomputed the near and far depth now. So that's how we check if it goes outside the camera, I guess. Cool, and then this was all about getting it to the screen, and I was in a very minimal way. Can we still do that? So I forgot about the image we had. I should have taken a screenshot. That bounding box. So we had that, all those points. Trying to remember how it looked. They're kind of aligned to the screen space in a way, but we don't know which ones are which. So we can't get a nearest point. So we just got to transform all of them. So there's this view to screen I've got where it just does some division and stuff and gets into, multiplies by the screen dims and stuff and gets it into screen space. Hey Alex, how's it going? Alright, yeah, have a good night, my friend. It's good to see you. Have a good night. Hope you have a good such weekend as well. Transform screen of view space. So yeah, I guess we'll call this 8 times. So in Arseni's blog, he does the same sort of thing, right? So he does it into takes a min and max. You divide by W. So after you've done the division, he does the min max, and then this bit can be done last after you've taken the min max. It's that final multiply and move. Okay. Yeah, I guess we've got to do this manually. So let's get rid of all this code. Goodbye. Well, min max points screen space. It's funny, you got some big old min and max functions, right? That's just gonna have to be a lot of them. So we're gonna be doing basically a bunch of like p0 dot xy divide, right? So p0 dot xy equal div with p0 dot z, right? Got to do a scalar version. And then I got to do that for all of them. Bunch of divides and stuff. 2, 3, 4, 5, 6, 7. Nice. So we copy all that. Nice. So after we've done the divide, now we've got to take a min and max between all these and find our min max in that sort of, what would you call it? Clip space. So now we're in clip space because we've divided by z. We can then min point clip space. So it's just a whole bunch of min vector 2s. So I think we'll just do pairs, something like this. 3 and 2. And then that pair of pairs will be minned. And then you got to do it all again with the next lot. And that quad will be minned again. So that's a 7, 6, 5, 4. And then we just do a lovely min. And voila. So there's your min point in clip space. And then your min point, or your max point. So everywhere we find min on this line is max. Boom. Cool. All right, what else? So now we've got to get into screen space. So we did have that sort of like transform code just somewhere here. So it's this code here that we need to run. So yeah, it's normalized device coordinates, isn't it? So NDC. Why did it say NS? Right, so let's take this and we'll say from clip space. From clip. So that'll be that code. And then this will call into this one. Screen dims, screen, clip space scale. Doesn't mean vector 3 anymore if it vector 2. And voila, so now we can got this thing to reuse. So we just do that twice. So it just scales it by how do I take it from clip space into screen space? It's a 1 divided by the height of the screen or something like this. And then we just offset it by half the screen dims because clip space's origins is in the center of the screen, whereas in the screen space for me is the lower left. So finally we just produce these screen space versions, which is min point, so screen dims, and then screen from clip space scale. Perfect. So again, we just take that sort of min and replace with max. Oh, nearly there. So this is just some extra stuff where we clamp. And yeah, so this should hopefully be a more optimized box. It'll be more costly because there's a lot more divisions going on, right? There's a lot more. You see, I wonder Oh no, yes, the divide by z's will be different, meaning that where they are on the XY on the screen could be different. Yeah. So there's a lot more divisions going on, so it's gonna be more expensive, but the box that we get will be better, especially when they've got a higher field of view. So let's see how that box looks. At least, is it right? Okay, so oh, that looks good. So here's what we ended up doing. So we used to go around the green box, which was a version of the red box, but then we took, so this red box is in local space of the object. So if this object rotates in the world, then obviously it will, this box will rotate as well. So we used to take this local space box and take the maximum points of it basically and make a view space bounding box for it, right? And then we used to put the screen bounding box around that. But now we've just taken all of these corners here. Well, we're taking this, we've got this transform which has the basis vectors of this in view space. So I guess it could go like back that way, up this way, and this way here to these sort of edges from the center. We produced the half vector which went diagonally, so it went up to this point here in this corner. We then subtract, so this was already like a view from local, so we're already sort of, we're operating in view space at this point. So these are all in view space. So P0 would be this one up here, because that's the, well, that'd be P1 because that's the add of that basis vector. Then down here would be P0. Then all we're doing is sort of adding the x, y, z of these basis vectors times 2 to the bottom left one down here in this case, and getting these corners here, this corner, that back corner, this corner here. And then from the P1, we're doing the subtraction and getting the other ones. So from this one here, we're doing a subtract, getting that one, and that one. And then from here, we basically just do the whole sort of like, get the min and max z. And then do the divide into screen space. And then do the whole sort of like min and max of everything and bring it, sorry, into clip space, min and max of everything, then do the bring into screen space, and there's our box. So I'm glad they ended up working, but there's probably some bugs, right? Can't be working first time like this. But some bugs that'll be too. Right. So actually sometimes it does. No, I think it's all around a smaller box. So yeah, that's going to be a nice smaller box there. That's way better. See, this, the box what it used to would have been all the way up here, across there, and down. So yeah, I wonder though. And in this case, right, it would have been like all the way across here and down. So we're definitely like, oh, for crying out loud, I already bugged that one up. So in this case, it's still kind of big, but it's better. So when it's like in the center of the camera, what can we say? Well, it's still better when it's in the center of the camera, I guess. Obviously, when it gets smaller though, it's not that much better. So I think we can. There might be some sort of like. See here, it's still around. So the reason why we've got to do a box though is because we're not really doing a. It's an ellipsoid, right? So it's. But we might be able to do some fudging of the maths a bit to sort of shrink this down a bit more. But at least it doesn't change so much for the projection as much as the other one did. Oh, it kind of does. So with this high field of view, these points are really far away and it really stretches that one, right? Whereas with the smaller field of view, that would actually shrink down. I wonder, right? So the time is, so I think we're okay for a bit longer. So if we could put the field of view in the settings and just see what that looks like. And then we'll go back to the other view that we have with tons of them and then test out the performance. So if we go to the settings, I've got my little encoder file where I can add some stuff. So field of view, I guess we could say like, you know, let's say as low as 30, but as high as 120. We've got it at 120 right now because I really wanted to test high field of views and see if my thing broke there, you know what I mean? Maybe it was a good idea, maybe it wasn't a good idea, but there we go. So let's move it down to 60 instead. And now we've got this sort of setting we can play around with. So I think if I just simply run a encoder script, and then we run the game. Oh, so that's code generator C file with everything ready. So in the graphics, where we have a field of view, oh, it's got a sort of like camera field of view thing, but screw that thing, right? Well, actually, the editor in that might want a different one. Maybe that could come from some other setting, but so maybe actually in game.c we should say field of view. Here we go. So this one will change. And this goes past the renderer. G settings, field of view. GFX, field of view. Well, it's because you haven't done this. Okay, so now we should be able to run this and have a programmable option to change the field of view, and we should be able to see it alter in real time. Right, it's definitely a much smaller field. It's way more zoomed in, isn't it? Oh my days. So, as you see when I go to the edge here, maybe we should get down to the box, meet it on its... Alright, so as you see on the edge here, it's not as stretched anymore. Maybe we can... Yeah. So if we open up the settings panel, we'll go to field of view, and we'll sort of just move this. Well, one would hope changing this would also change what we're seeing. I don't even know what's going on. Are we using the editor camera by now? Okay, it doesn't change every frame. That gets set in the initialization stage, so we need to put it here or something. Alright, let's try that again. So, hop down here. Alright, here we go. I could really get rid of that green box now, it's kind of useless. But anyway, that's where we're at. Oh crap. Right, so the field of view is making it zoom because I think I'm pushing... The field of view would make you seem more zoomed out, isn't that right? That's how it would work, because you've got the near plane gets pushed out and you're essentially cropping the image, isn't it? Yeah. Yep, that's true. So yeah, as you see, we're like a field of view of 45. Doesn't really move that much. But if we move out of the way here, so that top right corner of that red box, when we move it to the edge of the screen at 120, it really stretches out a lot more and produces a wider rectangle. So if we have a more zoomed in sort of box like this, we'll be restricting ourselves to how wide such things can stretch. Cool, so I think I moved it to 60. Now let's go to the game. Oh, sorry, the graphics side of things. Unfortunately, I undid all the things that I had, but at 25 and 4, I think we changed this sort of models thing. So on the Y, it would be divided by 8. And then we also needed to change the number of these here. So this means we can make a nice flat area, and that's generally testing what the game would kind of be like, or would want. So, right, we've just changed how we emit the ellipsoids now, so that we have 8 times less on the Y. Oh, don't mind me, I just left all my debug drawing on. So let's undo all that. So every ellipsoid was emitting its own debug drawing thing, which is top quality. So let's get rid of all that and have sensible performance. Okay, so now this is more of a, this is about 120,000 that we're pushing through the renderer, but so maybe we up that a bit more. I want to try 500,000, didn't I? Why has the performance got worse? Right, the stream held up. Did the performance get worse? Luckily I kept the old code. So that's 120,000, but we're only rendering 20,000 there. Like actually rendering 20,000 that come through to the renderer. After all the occlusion culling and that. About 4 milliseconds. This opaque render. But we made a smaller box. Okay, so if I up... Oh crap. That's strange. So if you look here, the amount that got binned is 21,000, right? And so the amount that actually got rendered that passed the occlusion testing is 21,000. There's about 140,000 here. As we increase this, there's a certain point when it just becomes too much. But this number didn't change here, which is confusing. So it makes me believe that one of the view space bounding boxes is wanting to do the whole screen. And what we actually have is a bug in the new... What we actually have is a bug in the way the bounding boxes are being in the new bounding box code, which is causing one of these to really cover the whole screen, and that's actually making the performance far worse. Okay. Oh, I guess we can take a quick look into it. Core shared. There was like a... So the old one... So when we're doing all these divide by Zs, if there's nothing kind of behind the camera, it's all kind of off the screen. I guess the best we can do is just see. Hmm. Right, let's go back to that one. Graphics. Yeah, go back to that one by one entry, and we just sort of play with that box a bit. I gotta bring back all those debug boxes because if not, it's not gonna work, is it? So we get rid of that view space one. We don't need that one anymore. Just keep the new screen space one in the original local space bounding box. And we look at this and see sort of like, well, if I move it out the screen, is there anything that can cause this to go absolutely haywire and huge? Oh, that right there, can you see it? It's covering the whole screen. Isn't that crazy? So yeah, it's got a thing right where it clips it to the, so it never goes off the screen. There's a pixel on the edge there. That's kind of cool, right? But then like that kind of snapped off there. That's interesting. I don't know what code is causing that. Right, something to look into. And then when you go sort of far away from it, enough away from it, it's kind of there still. So, bit annoying. But yeah, something to do with this code here, I guess. I wonder, so since we've only got one of these, we can print the crap out of these things. And you can save it. Behind. And then like near or something, you know. So if near and far show up, it means it got clipped. I've got to limit this for my compiler because it's shared between CPU and GPU, you know, all the fun of sharing code between CPU and GPU. So yeah, I could have maybe made that an ifdef or something somewhere else. Just call it print or something, printf. Right. Yeah, why didn't I call this thing printf? Anyway. The other one is here. outside. Yeah, let's call it outside for now. So we'll see where those can fail. Now, where else can they fail? They just get occluded. There's infinity or something as well. Let's try those out at least for now. I think I got to if def this. Why have I not defined this as 1 in my compiler? Might be a problem. Oh crap. Oh bugger. Right, let's define this up here. Then undef it. Ah. What is that buffer set to? 0, 1, 2, 3, 4, 5. Done. Right. Finally. Right, so outside is clearly what's messing around. It's not outside at that point. So what is causing it? Why is it one of the points? Can't be. Alright, let's look at that again. So it clips out too early, that is for sure. Right, so what's interesting is this one and this one, as soon as one of those two go, but this one's still in there, right? So am I getting... Are all those points really... They must be playing into effect of making the box because... Right, I got a bit of a weird one here. Any of those is greater than... Oh yeah, that should be alright. Screen dims. Scene dims F. Move this around a bit. Which one is it? I don't think it's really a specific corner, it's just the amount it goes off by. Yeah, it's a bit strange. Scene dims. We are rounding it by a pixel though, right? Where is it? Well, the rounding happens here. What? Yes, we definitely want to floor this thing. But this is not going to be what's contributing to the problem, because it's still... Yeah, no, it's not going to help. Right, so if any of the x and y's from the minimum are greater yeah, so the y wouldn't have been... Neither would the x been as well. I wonder which one of those it is. We could do this. So know if it's outside x or outside y now. That's outside x. Apparently it's definitely outside x. So what's interesting is we can tell that the scene dims is a perfectly fine. Ooh. Yeah, it's a perfectly fine number because the edge gets clamped in between there, which is what we do at the bottom here. Now I'm thinking maybe some of the divide by z's end up giving us strange values because they're off the screen. Is that even possible? Like, okay, so I guess at this point, why don't we print out what this value is? It might... Maybe there's like an NaN in there, or a... I don't know, what would it be, like a infinity or something? Interesting. So it'd be good to just like actually just print this out all the time. Just see what it is. Oh, to be serious. So the resolution is we can get the resolution by bringing up the profiler. It's 1920. 1080, right? There's no way that's 8 pixels out. There's no way that is 19. Right, so are all the threads getting something different? Like, what's going on here? Why is... There's only one ellipsoid. Why is there like a million threads going through here? That's a bit weird. B, there's 1855. That's more sensible number. So, what's going on there? Well, you got 32 threads coming through here. Local X. Go over all the ellipsoids, skip 32. Oh, right, of course. So I think the bounds of the... Right. The problem is this is actually running on the problem is the whole model instance is actually failing the test. For some reason that box is different. And that's the one that's failing. Right, I see some slightly different colors here. Interesting. Let's just do like a color blue and then a color green. So those more sort of colored ones is going to be the instance. Oh, that instance is really wrong, isn't it? Oh, wow. It's only half the... Interesting. So if we take the... Why is it so wrong? But yeah, I guess we'll save that one for the next stream. Interesting. Yeah, so there's something wrong with the view from model matrix for some reason, but then not when you combine it with the ellipsoid. Yeah, there's something to look into. That's the reason why it's sort of clamping off the edge. And then we've got a problem where if we turn it back around the other way, it can like take up the whole screen and that makes performance terrible. There's something to look into as well. Right, so next stream will be on Sunday, where we carry on with this sort of performance tuning and just seeing sort of like what sort of numbers we can get. And yeah, that's about it. There's Discord if you want to come and hang out in the meantime. And chat offline. And let's find something to read quick. Let's give TCAP a read. Okay, guys. There we go. Right, have a good evening. Hopefully you have a good weekend as well. And yeah, hopefully see you all Sunday. All right, to catch you later.